Have you ever just looked at your phone or your computer and wondered what's really going on inside? What actually makes it all tick? Well, today we're going to pull back that curtain. We're going to demystify the fundamental pieces that make it all possible. Let's dive into the building blocks of modern electronics. All right, so if you've ever even glanced at an electronics syllabus, you've probably seen a list that looks a lot like this one. And yeah, words like electromagnetism, transistors, and capacitors, they can seem pretty daunting. But don't worry, our whole goal here is to connect these dots and show you how all these concepts fit together in a way that actually, makes sense. Every system has rules, right? And electronics is no different. Before we can really get a handle on the individual parts, we have to learn the rules of the road, the laws that govern how electricity flows, and that whole foundation is built on something called Kirchhoff's laws. So, Kirchhoff gave us two simple but incredibly powerful laws. The first one, his voltage law, or KVL for short, is all about voltage, that electrical pressure, as it moves around a complete circle, what we call a closed loop. The second one, his current law, or KCL, zooms in on the flow of electricity at any single intersection, or junction. Okay, let's dig into that voltage law. KVL basically just says that energy is conserved. The total voltage you supply to a circuit has to be completely used up by all the components along that path. It's kind of like a balanced budget. Every single volt you put in gets accounted for. Or an even simpler way to think about it is what goes up must come down. And here is a perfect example. We've got a 100-volt battery powering this circuit. Now, as the current flows, it goes through 3 resistors, and each one causes the voltage to drop. The first one uses up 50 volts, the second one uses 30, and the third one takes the last 20. And if you add those up, 50 plus 30 plus 20, what do you get? Exactly 100. The voltage supplied equals the voltage used. That's KVL in action. Now, for Kirchhoff's second law, the currents law, or KCL, this one is all about flow. It's super simple. At any intersection in a circuit, the total amount of current flowing in has to be exactly equal to the total amount of current flowing out. Think of it like pipes with water. You can't have more water leaving a junction of pipes than what came in. Nothing gets lost, and nothing is magically created. Look at that central point P right there. It's acting just like a busy traffic circle. And KCL is the rule that prevents a total traffic jam. The currents flowing in, that's I1, I3, I4, and I6, they all have to add up perfectly to the currents flowing out, which are I2 and I5. The flow is always, always balanced. It's such a simple, elegant rule, but it is absolutely essential for designing circuits. Okay, so now that we've got the rules of the road down, we can start looking at the actual components. And first up is a device that's designed for a very specific, very important job: storing energy. So let's talk about storing the spark and how capacitors work. So a capacitor, at its very core, is an energy storage device. It holds onto that energy in an electric field, almost like a tiny rechargeable battery. But here's its superpower. Unlike a regular battery, it can release all of that stored energy in a sudden, incredibly powerful burst. Now here's where it gets really interesting. How you wire these things together completely changes their behavior. If you connect them in parallel, side by side, their storage capacities just add up. Simple enough, you get more total storage. But if you connect them in series, end to end, something really counterintuitive happens. The total storage capacity actually goes down. So let's see why that is. These diagrams show us exactly what's going on. In the parallel circuit on the left, each capacitor gets the full voltage from the power source, so they all charge up on their own and their capacities just add together. But look at the series circuit on the right. Here, the charge has to kind of jump from one capacitor to the next. The charge on one plate induces a charge on the next one, which basically makes the gap between the plates bigger, and that reduces the overall ability to store energy. So why does any of this matter in the real world? Well, think about a camera flash, that super intense, brief burst of light. That is all powered by a capacitor. It slowly, patiently stores up energy from the battery, and then when you hit that button to take a picture, bam! It dumps all of that energy instantly into the flashbulb. So we can store energy, but how do we control it? Well, that brings us to what is arguably the most important invention of the 20th century. We're talking about the tiny gatekeepers that form the foundation of all digital logic, the transistor. Okay, so a transistor is a semiconductor. That's a special material that can be told to either conduct electricity or block it. And it can act as either an electronic switch or an amplifier. And here's the magic trick.
A teeny tiny electrical signal sent to one part of it, called the base, can control a much, much larger flow of current through the rest of the device. The absolute best analogy for this is a valve on a big water pipe. Think about it. A small, easy turn of the handle can control a massive, powerful flow of water. Well, the transistor does the exact same thing, just with electricity. A tiny little input signal precisely controls a much more powerful current. So on the left, you can see the physical component, and on the right is its symbol in a circuit diagram. And both show the three crucial parts. The base, that's our controller, that's the valve handle. Then you have the collector and the emitter, and they form the main pipeline where the big current flows through, just waiting for the base to tell it what to do. So what do we do with this amazing little gatekeeper? Well, it has two fundamental jobs. First, as a switch, it can turn a current on or off billions of times a second. And that's how we create the ones and zeros that are the foundation of all digital information. Second, it's an amplifier. It can take a tiny, weak signal, say from a microphone, and boost it until it's powerful enough to drive a massive speaker. Pretty incredible. Okay, so we have our rules and we have our key components. But what makes it all work? Well, for that, we need to kind of zoom out and look at the invisible forces that are actually carrying the signals. And this is the world of electromagnetism and waves. I mean, we've all felt it, right? That invisible push and pull from a magnet. The iron filings here are just tracing out that field of force, which we call a magnetic field. What's so amazing is that this very same force is what makes everything from electric motors to wireless communication even possible. The real game-changing discovery came from a scientist named Hans Christian Ørsted. He figured out that a simple electric current flowing through a wire creates its own magnetic field all around it. This was a monumental realization. It meant that electricity and magnetism weren't two separate things at all. They were a single, unified force, electromagnetism. And there's even a pretty cool trick for visualizing this invisible field. It's called the right-hand rule. If you just imagine grabbing a wire with your right hand and your thumb points in the direction the current is flowing, your fingers will naturally curl in the exact direction of the magnetic field. It's a simple little trick, but it's incredibly useful. Now, this beautiful dance between electricity and magnetism leads to something amazing: waves. A changing electric field creates a magnetic field, which in turn creates a new electric field, and this chain reaction just keeps going, spreading out through space. This self-sustaining disturbance is an electromagnetic wave, and it carries energy and information across huge distances. And the result is this vast electromagnetic spectrum. It's all the same type of wave, just with different wavelengths and different amounts of energy. Down on the left, you've got these long, low-energy radio waves. As you move toward the middle, you hit infrared, and then that tiny little sliver of visible light that our eyes can actually see. And if you go further to the right, you get to the really high-energy, penetrating waves like X-rays and gamma rays. Your Wi-Fi, your cell phone, your microwave, it all works by harnessing a very specific piece of this spectrum. So, there you have it. From the basic rules of Kirchhoff, to the energy-storing capacitor, to the gatekeeping transistor, and finally the electromagnetic waves that carry all our signals. These really are the fundamental building blocks of our modern world. And now that we understand how they work, it leaves us with just one really exciting question. What are we going to build with them next?